So back a few videos ago, I sort of made up this sort of problem where I put 1 coulomb of charge on two parallel plates, and I said that there was an electric field of 540 newtons per coulomb over 3 centimeters, and I went from there. And so let's go and sort of look at this. That was a capacitor before I had explained what capacitors are. So let's use those numbers. So as you know, change in V equals negative ED. And so I said that if I've got negative 540 newtons per coulomb times 0.03 meters, I'm going to end up with a change in voltage of negative 16.2 volts. I already did that calculation, so I don't really need to punch it into my calculator again. Okay, and then I said that I put 1 coulomb of charge on the capacitor. Okay, well, let's plug those into my potential energy. My potential energy my potential energy, oh, it's going to be 1/2 that. Oh, yeah. So up here, my potential energy was wrong because I forgot the value of 1/2. Okay, so wrong, forgot 1/2. Okay, so let's talk about that. Okay, and the reason is that okay, as the capacitor discharges, well, then that Q that's on the capacitor is going to sort of meet up with its opposite Q, and they're going to neutralize each other, so the Q is going to go down, and as the Q goes down, the V goes down, and so at the end, when the capacitor is completely discharged, there's not going to be any Q on the capacitor, there's not going to be any V on the capacitor, and so when it's full, it's got Q times V. When it's empty, it's Q times V, and the total energy, it's 0 times 0. I'm sorry, when it's full, it's Q times V. When it's empty, it's 0 times 0, and so the overall potential energy for the entire capacitor is going to be the average of QV and 0, which is going to be 1/2 QV. Okay, so then we're going to end up with a potential energy of 1/2 of 1 coulomb times 16.2 volts, so we're going to get 8.1 joules. Okay, but now I want to figure out how big is my capacitor. So I'm going to plug that into C equals Q over V, and so my capacitor, when it had 1 coulomb of charge on it, it had 16.2 volts. So my capacitance is going to be 1 coulomb divided by 16.2 volts, 0.062 0.062 farads. So I just sort of made up off the top of my head a few lectures ago what turns out to be a 0.062 farad capacitor. And now let's look at that result and let's plug it into C equals epsilon naught A over D, and let's solve for how much area I would need to make that capacitor work. And let's see if I'm anywhere reasonable whatsoever. My guess is I'm probably not. So I'm going to rearrange that for A. I'm going to get A equals C times D divided by epsilon naught. So my area is going to be 0.062 farads, and my distance was 0.03 meters, divided by my epsilon naught, as I said before. Let's see if I can find it again. It is 8.85 times 10 to the negative 12th, and that's what gives me, that's what really scares me, because it's a really, really, really big number in the denominator. It's a really small number in the denominator. So 0.062 times 0.03 divided by 8.85 second EE negative 12. I get my area of a plate is 2.1 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters squared. Okay, and so that's not reasonable. That's a square. That is, if I take the square root of that, that's 14.5 kilometers on a side. So this is not reasonable. So in one of the videos they talk about how a 1 farad capacitor is really, really, really huge. And a 1 farad capacitor is really, really, really huge. So so basically you're going to be seeing capacitors that are microfarads, nanofarads, and so you're going to see microfarads, nanofarads, and picofarads. Okay, and in the next video I think we're going to make an estimate of how big the capacitor in the do-it-yourself video, how big was that capacitor.